Maths of the Coronavirus, Part 7, Toilet Paper. No discussion of the coronavirus would be complete without a discussion of toilet paper. Of all the bizarre things that have happened, the panic buying of toilet paper would have to be up there amongst the strangest. Running out of toilet paper has been a real problem for many people, so it's probably a good idea to know how much you have left. And maths, of course, can help you with that. To figure out how much toilet paper you've got left on a roll, the first thing we need to do is to create a mathematical model. What is a mathematical model? Well, what we're going to do is we're going to take something from real life, like a roll of toilet paper, and we're going to create a version of it that is, 1, simpler than reality, and 2, made up of maths ideas or shapes that we can do something with. So let's take our roll of toilet paper for example. Look at the roll end on, and you can see some shapes that we're already very familiar with. It's much easier to see this if we use a graph. So here's the same roll of toilet paper, but put underneath a Cartesian plane using Desmos. The first thing we can see is the circle in the middle, the cardboard roll. Now circles are good. We know things about circles. Moving out from the roll, we get to the paper, and it's wrapped in a series of layers. If we could zoom in some more, we'd see that the wrap is very much a spiral. But for the purposes of our model, remember models are simpler than reality, we can treat our roll of loo paper as a series of circles getting bigger and bigger and bigger, but which all have the same centre. This is what we call a set of concentric circles. Now, it's going to be much easier to work with that model if we remove a lot of the mess. Now that we've got the basics, let's remove the mess and even remove the original picture. That's better. Now we just have the circles. Before we jump into making our model a bit more usable, let's remind ourselves what we know about circles. Circles have a radius, a diameter, and a circumference. They have other things too, but we don't need to use those here for our model. And we're only going to need one formula, and here it is. It's the famous formula for the circumference. The circumference, the distance around the outside, is equal to pi times the diameter. C equals pi d. So let's look at the circles in our model. The circumference of the cardboard roll is pi times d. And if I wrap the toilet paper once around the roll, the length of paper I've used is the same as the circumference. So the circumference is going to be a great hint as to exactly how much paper is left on the roll. So we wrap the toilet paper like that, and then we keep wrapping around and around. But every time we wrap another layer, the roll gets thicker. In maths terms, the diameter is getting bigger. And of course, if the diameter gets bigger, so does the circumference. Basically, every layer of toilet paper on the roll is longer than the layer before it. And you know this. All of us at one time or another have looked at the nearly empty roll, thought we had enough, but because the last few layers of the roll are really short, it turned out we actually didn't have enough. And now some algebra to go with it. Now, how quickly the roll gets thicker, of course, depends on how thick your paper is. Now, that's going to be a millimetre or a fraction of a millimetre. But in any event, let's call the thickness of your paper T for thickness. The diameter of the cardboard roll in the middle is going to be D. So when we've wrapped the paper round once, the first layer, the diameter is going to be the original D plus a thickness of paper on either side. In algebra terms, that's D plus 2T two thicknesses of paper, one on the left and one on the right. The next layer adds another thickness of paper on either side. So we go from D plus 2t to D plus 4t, then D plus 6t, and so on. To find the circumference of each layer, and therefore how much paper is on each layer, just take that diameter and multiply it by pi, because the circumference equals pi times the diameter. So laying each of those layers out in turn, what you've got is what we call in maths a sequence. That is, a set of numbers in order that we could describe using a particular rule. So the diameter of each of those layers is D plus some number times t, D plus 2t, D plus 4t, and so on. So let's lay that out in a bit of a table and look at the layer count and this concept of some number times t. So n here is the number of layers. Where n equals 1 layer, the diameter is D plus 2t. Where n equals 2, it's D plus 4t. Where n equals 3, it's D plus 6t. And then it doesn't take a maths genius to figure out that the number in front of the t is just twice whatever the n number was. So if n was 4, it would be D plus 8t. In general, we could say that the diameter at any given layer is D plus 2 times n times t, or D equals, that's capital D, equals D plus 2nt. And then in general, if that's the diameter of a layer, the circumference of that layer is just pi times that. Pi times D plus 2nt. There's an awfully large number of variables in all of that. So let's take a step back a bit and put some numbers in instead of the variables so we can get an idea of how this sequence works. For this demonstration, I've made the diameter of the cardboard roll 40 millimetres and the thickness of a sheet of toilet paper 0.5 millimetre. Now, they may not be super accurate numbers, but they'll do for the purposes of our demonstration. Always remember, of course, to keep your units of measure consistent, everything in millimetres in this case. So layer 1 has a diameter, D sub 1, of 40 plus 2 times 0.5, which is 41 millimetres. The circumference there, C sub 1, is 128.81 millimetres, rounded off to a couple of decimal places. D sub 2 is 40 plus 4 times 0.5, which is 42, giving me C sub 2 of 131.95 millimetres, again to a couple of decimal places. And you can continue adding layer and layer and layer. And if we present those numbers in a table, similar to the one we saw earlier, you can see that the circumferences of the layers form a set of numbers in order that we can describe using the rule that we created earlier. That is, C sub n equals pi times D plus 2nt. So this set of numbers is, therefore, a sequence. Before we go too much further, let's make sure we're comfortable with this concept of a sequence. Remember, a sequence is just a set of numbers in order that can be described by a rule. The thing is, you've been working with sequences since kindergarten. You just haven't called them sequences. Take this one, for example, 2, 4, 6, 8, 10. The first term in the sequence, that is n equals 1, is 2. The second term, where n equals 2, is 4, and so on. And it's very easy to make up a rule for the nth term, t sub n, because every term is just 2 times whatever the n value was. So t sub n, the nth term, is just 2 times n, or 2n. How about this one? 3, 5, 7, 9, 11, and so on. Now that one, of course, is just all that numbers in the first sequence with 1 added to them. So the rule for the nth term is going to be t sub n equals 2n plus 1. Pause the video for a second and see if you can work out the rule for this sequence, 2, 6, 10, 14. I hope you did pause the video and that you worked out that the rule for that sequence is t sub n, the nth term, equals 4n take away 2. And that brings us to the end of the first video. Unfortunately, we haven't as yet answered the question, how much toilet paper do I have left on the roll? We know how much is in each layer of the toilet roll, but to figure out how much is on the roll all up, we're going to need to add up all those circumferences. To do that, we need to introduce another mathematical idea called a series, and that's the subject of the second video.